everyone. Welcome very much to the PhD presentation and defense by Chris Aucoin. I'm going to be serving as host today at the meeting, and Carl will do more formal introductions of Chris's committee and other visitors who are here today. I think one of the advantages of doing it online, of course, is that we can ask questions through the chat, and I think anyone should feel free to pose a question in the chat at any time during Chris's presentation, and I'll get to these when we have the Q&A after he's finished. And then after Chris's presentation, we'll do a question and answer session, and because the room is full of experts, so should be very interesting, should be very good, and who knows, might be long lasting. And then Chris, you'll transfer the host maybe to me. We'll exclude you from the meeting.
Yep.
And participants will convene, and then we'll invite you back into the space after you're finished.
All right. Yeah, you'll have to tell me how to do that when we get that far. So.
Okay, very well. So without further ado, Carl, would you like to do a formal introduction, please?
Of course. Yeah, well, happy Flag Day, if that is a real holiday. And of course, welcome to all of you. Thanks for coming to this presentation of some of the research of Christopher Aucoin. I'm always proud of all students, but particularly those who persevere through sometimes difficult times and come back and finish off. Let me welcome members of Christopher's committee as well. First of all, the outside external committee member is Professor Andre Desrochers. I don't know if he's here yet, from the University of Ottawa. And of course, Dr. Ben DiTillo, himself a PhD from this department, who's now at Purdue University, Fort Wayne. The departmental members include Dan Sturmer, Warren Huff, also I think not here yet, and Arnie Miller, who joins us from Long Island, and myself, of course. Well, I first met Chris in 2012 when he enrolled as a master's student here at UC, and I got him going immediately on field work in Kentucky and found him to be a very engaged, intelligent, well-organized student with some curious quirks. At that time, at least, he only ate chicken nuggets. I don't know how he could survive that way, but you see he's here and still healthy. He had a good background in research as a result of his undergraduate studies. He graduated with honors in both geology and anthropology from the State University College at Oneonta, New York. And during this time there, he did some interesting undergrad research on archaeology at the State Museum in Albany, which is near where he lives now. And he also conducted, with some others, a study of digital mapping of dinosaur trackways, of all things, in the lowermost Jurassic near Holyoke, Massachusetts. That paper eventually made its way to the great journal Paleontological. But he decided he was most interested in Paleozoic invertebrates and stratigraphic paleontology. Well, I guess maybe he had no choice, right? Anyway, there he is. And he completed a good master's thesis in the summer of 2014, which dealt with some aspects of taphonomy and sequence stratigraphy and parts of the Upper Ordovician famous Richmond group around here. And that time, he had, during that time, he had made good friends with some of the dry dredgers. A shout out to them. I don't know if any of them have joined. Oh, Don Bissett is here. And they not only provided material, but excavated quarries for him and provided several grants that helped him out, amongst other things. I was always impressed during his time here that Chris took considerable initiative to expand the scope of his research. He presented talks in meetings, both nationally and internationally. And during one in 2013, he made the acquaintance of researchers in Canada, Andre, who I've mentioned before, in Poland and in Germany, notably Axel Municki. And eventually he went to work for a time at Municki's lab to study carbonate petrology with the aid of some AAPG and Clay Mineral Society grants. And I was impressed that by 2014, those folks had some of them invited him to come back to Europe, and he did spend time there to study some of the analogous or hopefully correlative rocks, and in fact identified an unconformity that may well be the same one that he helped to document here in the U.S. He also learned a lot about carbonate petrology from Axel in his lab, and acquired skills that he put to good use in studies of well-preserved gastropods, which are a chapter of this dissertation I think he's not going to talk about today, but a very interesting piece of work. Subsequently, Chris took the initiative to apply for a Fulbright fellowship, and in 2015, 2016, he spent the year at the University of Ottawa in Ontario working with André Desrochers, an expert on petrology and stratigraphy of Paleozoic rocks, and he was able to make a good use of this time to make detailed correlations into some newly acquired cores from that area. He also spent time and gained good field experience with Professor Desrochers and his students in the Ordovician of Anticosti Island, Quebec. All in all, Chris's research has resulted in some 7 peer-reviewed papers. A couple of them are chapters of this thesis, a couple of guidebook articles, and more than 25 abstracts. Today, Chris will present some aspects of his PhD dissertation dealing with sequence, lithostratigraphy, and chemostratigraphy of the Upper Ordovician Richmondian, which I might add is not just any time. It was a time of substantial volatility of environments and faunas, the time of the Richmondian invasion, when we see a bunch of new taxa arriving in the local area, and possibly in other areas we see the effect of this biotic change as well. And moreover, this is really the lead up to one of the greatest mass extinctions of all time in the Hernantian. So understanding the conditions that prevailed prior to that are very key in understanding biodiversity crisis and so on. I think I'm getting a lot of feedback. He tells me that I should shut up, and I will. I just want to move now to Chris Aucoin and his research, and thank you. And I will mute myself and my extra blather. Thank you.
Thank you for that wonderful introduction, Carl. I'll just figure out how to share everything here properly. Let's see. Screen 2. Can see nothing at the moment. Let's see. Slideshow. I don't know. Maybe Carl, just give me a nod. You can see everything fine. All right. Cool. All right. So thank you all for coming from all parts of North America at the moment. So obviously, I'm Christopher Aucoin. I've been working with Carl for a number of years now. When I first met Carl in Cincinnati, I had to admit I thought I was going to be working on some Devonian trilobites in Morocco and going on some nice exotic field trips. Ultimately, I ended up going to the exotic areas of Kentucky and Indiana and Ohio. But I have to admit this project has been a lot of fun. I originally intended my PhD, like I was going to work my master's with Carl in invertebrate paleo and stratigraphy, and then I was going to run off and do dinosaur research, and you can probably see some of the dinosaurs still hiding behind me here. But I fell in love with the work I was doing with Carl and decided to stick around and continue. So as Carl pointed out, I'll be talking to you about some of my dissertation chapters, primarily focused on the Upper Ordovician Richmondian, and really looking at some of the fine-grained or fine-scale stratigraphy and chemostratigraphy, paleontology, and so forth. Before I get into everything, I just want to thank the numerous funding sources. Carl already mentioned a number of these from my Europe trip and so on. And again, I especially want to thank the dry dredgers. I know a couple of you are here. The dry dredgers have been probably my #1 supporter financially, as well as just in pure enthusiasm for the work I was doing. So internally grateful to the dry dredgers. Alrighty. So again, as Carl mentioned, I've been focused on the Upper Ordovician. So I'm admittedly a little bit biased, but I find the Ordovician to be a particularly interesting period in geologic time. And there's a number of reasons for that. Let me just continue here. I'm going to get my laser pointer going. So at the beginning of the Ordovician, as many of you probably are aware, we have, and I apologize, I always have trouble pronouncing this, we have the Great Ordovician Biodiversification Event. And so if I bring it up for the rest of the talk, I will refer to it as the GOBI for short. And what the GOBI is a drastic or a pretty rapid increase in biodiversity at the beginning of the Ordovician. So what this diagram is here is diversity of genera through time as derived from the paleobiology database. And so at the beginning of the Ordovician, we have this great increase in diversity. And then if we head to the end of the Ordovician, we see quite the opposite, where we have the first major mass extinction recorded in the fossil record, known as the end Ordovician extinction. So on one end, we have increase in diversity. On the other end, we have sudden extinction. And the interval I'm studying is the Katian, more specifically the Richmondian. And so we're situated in an interesting place temporally, where we're in this transition from diversification to extinction. And so if we can understand what is going on during this particular time slice, it may eventually lend some details as to why we're going from diversification to extinction. So for some paleogeographic context, we're on the paleocontinent of Laurentia, specifically in the Cincinnati Arch. The formation that I'm most focused on is the Waynesville Formation, named by Augustus Firsty in 1908 for the type section near Waynesville, Ohio, so northeast of Cincinnati. He also named its three members, the Fort Ancient, Clarksville, and Blanchester, for towns also in similar region. Now, the Waynesville is interesting in its own right, and not only for its, again, being situated here in that transition period, but the Waynesville has within it a biological event known as the Richmondian invasion, which I'm sort of illustrating here with the arrows. And so the Richmondian invasion, as Carl alluded to, is a biological event where we have roughly 100 taxa, give or take, moving into the Cincinnati Arch region, primarily from elsewhere. Some of those taxa are ones that may have been rare in the Cincinnati Arch prior, but suddenly they are proliferating and become commonplace. And so this is, a particularly interesting topic. Why do we see all these taxa moving into the Cincinnati Arch region? And I would be remiss for not shouting out Dr. Alicia Stegall and her lab at Ohio University. They've done a lot of fantastic work studying the Richmondian invasion. And it is my hope that this fine-grained stratigraphic work that I'm doing will assist them in the type of study they're doing on the Richmondian invasion. And just before I go, I should have mentioned this earlier. We are at this time located primarily south of the equator, the paleocontinent being primarily south of the equator, with Cincinnati Arch being about 40 degrees south. So when I came in as a master's student, the first part of my project really was trying to tackle the diverse nomenclature that went along with the Waynesville Formation. For the longest time, the stratigraphy of the area has been sort of studied from a state line boundary perspective. Ohio had their names for the units, Kentucky had their names, Indiana had their names. And so we had a whole series, and I could throw up a diagram that would have different names that would span the whole screen that are all talking about the same interval. So the primary focus of my master's, and I continued to revise it in my PhD, was to take these diverse nomenclatures and try to simplify it as best as possible in a way that we could all correlate these units across the state boundaries and use them in the same way. Now, as a result of this project, I discovered something that I was not expecting. And Carl alluded to that as well, and that's the mid-Richmondian unconformity, as I call it, which is this quite sizable chop surface situated below the upper member of the Waynesville Formation, known as the Blanchester. Now, this image is from more proximal deposits, and what you can see is under the mid-Richmondian unconformity, we eventually, as you move further and further south, further near shore, we have a complete chop of basically 2/3 of the entirety of the Waynesville Formation, and potentially even into the units below. So this is, quite a sizable uniformity surface that, for the most part, has not really received much attention in the past. Now, back in, I think it's 2000 or 2002, a pair of bryozoan workers, Ross and Ross, in the course of their work correlating bryozoan occurrences, did suggest that there was some sort of mid-Richmondian unconformity, though their stratigraphic correlations and the framework we work with do not match up. So I think they were on the right track, but I think we have a more refined version of what the stratigraphy looks like and a better placement for it. And so, of course, one of the questions as I've been going through this project is wondering, is this unconformity strictly a local phenomenon, or can we see it elsewhere? Alrighty, before I get into the meat and potatoes of this talk, I just want to quickly talk about sequence stratigraphy, because for any of you, which I think is quite a significant number of you who have worked in the Ordovician, you know that we often discuss the stratigraphy in terms of sequences. So to be brief, a sequence is basically a complete cycle of sea level rise and fall, or at least relative sea level rise and fall. And it's usually subdivided into 4 stages. Here in the Cincinnati Arch, we typically just look at 3 stages. The low stand, which is typically the basal stage of a cycle, we don't really find evidence for it here typically, so we don't really look at it. But on this side of the diagram here, we have in red what's called the TST, or the transgressive system strat. This is where we have sea level rise, relative sea level rise exceeds rate of sedimentation. So in these areas is where we're going to find our max carbonate material, our larger shelly beds and things like that. Our sequence boundaries, which mark the base of the TSTs, is where we're going to generally find our unconformities like the MRU. For example, the mid-Richmondian uniformity, as I just mentioned, is right here, and we have the TST overlying it. In blue, we have the HSTs, high stand system strat. This is where sedimentation rate starts to exceed that of sea level rise, so we're going to start seeing thicker shale deposits in the more distal environments as that sediment is no longer being sequestered in the near shore. And then we have in yellow the falling stage system strat, which again, they're pretty thin around here. We often incorporate them with our HSTs, but this is an even more rapid rate of sedimentation, and we start to see more silt deposits and things like that. Slightly coarser grains make it out into the distal environments. And so for the longest time, Ordovician workers have been sort of working with the Holland diagram that he developed, Steve Holland developed in the 90s, which subdivided the Ordovician into a series of sequences, C5, C4, et cetera, and through the work that I've been doing, the work that Carl's been doing, the students that were working with Carl well before me, we've been working on redefining the sequence strat framework of the Upper Ordovician, and that's culminated in this paper that came out last year, Brett et al. 2020. And I'm only showing partial of that diagram, but it involved redefining and further subdividing a lot of the original Holland sequences. So just to sort of highlight the interval we're going to be looking at, we got the Waynesville here, and that is subdivided into 4 different sequences. We got the C5A at the base in the Fort Ancient. C5b. Right above it, also Fort Ancient. The Clarksville member is the C5c. The upper member of the Waynesville is the Blanchester, which is the C6a. And then I will talk a little bit about the Liberty, which will be the C6b. So as I already sort of mentioned, the main focus of this project was to really create a fine scale record of what the Richmondian invasion and the mid-Richmondian unconformity look like, in order to start asking some of these more specific questions. For example, is the Richmondian invasion strictly a local phenomenon, or do we see it globally as well? It certainly serves that if we have taxa migrating into one region, that there could be taxa migrating into others at the same time. So it's an interesting question that is worth exploring. Another question, how many phases do we see within the Richmondian invasion, and how specifically can we correlate them? Does everything come in at once, or does it come in a series of pulses? Do those pulses line up with various sequence boundaries? Do they have any correlation with the mid-Richmondian unconformity, and so on? So there's a whole host of questions one can ask when you get a finer, detailed look at the stratigraphy. So for the next few slides, I'm gonna give you a whirlwind look at the stratigraphy of the Waynesville. I can't go through all of it because we'd be here for the rest of the time just going through the stratigraphy. So I'm going to just focus on what I believe to be some of the more significant units. All right, so as I mentioned earlier, when I first started, my goal was to take the nomenclature and simplify it. And of course, my way of simplifying the nomenclature was to come up with 12 new names that no one had ever used before. And so what I did is I took the Waynesville and its 3 members and subdivided those members into even finer packages that we call subnumbers. And so we came up with 12 different submembers for the Waynesville that we can correlate from east to west of the arch, as well as from the distal offshore environment to the more proximal nearshore. So for the next several slides, we're going to have the submembers on the side here, a little red box sort of indicating roughly where we are in the column. And I'll also keep this line here just to indicate where that mid-Richmondian unconformity is, so we have that perspective. And I'll also include this little ramp diagram so you can see when we're in the distal versus proximal environment in the event that I forget to mention so. So in this image here, we're in at Southgate Hill near St. Leon, Indiana. And we're looking at the basal part of the Fort Ancient member of the Waynesville. So at the base of the formation, we have what's called the Southgate Hillbed, named for this location. It was Steve Holland's selection for the major C4, C5 sequence boundary. And in St. Leon, the Southgate Hillbed is roughly about 1 meter thick. And it contains abundant Cincinnati crinus, a bunch of Cincinnatina, that's this brachiopod here. You'll see a lot of Cincinnatina throughout the rest of the top. It can be somewhat reddish in color from phosphate and rusted pyrite. And it makes a pretty good statement in this outcrop. As I'll show in the subsequent image, as we move more proximally, we can see this bed make really nice sharp contacts as well. But it's really an interesting unit because when we're looking at it in between, it can sometimes become rather diffuse. Specifically, if you go to Cedar Creek, Ohio, which is actually pretty close to type Waynesville, this unit looks not like much of anything. It sort of looks like an extension of the Arnheim below. So it's a rather interesting unit. Overlying that, we have the lower Fort Ancient shale, which is a rather thick shale package, 6 meters at this locality. And it remains pretty thick in most parts of the arch. The other name the shale goes by is the Barren Shale because we don't really see much in the way of fossils in it. You can find some Cincinnatina micae and some other bits and brachiopod and so on. But for the most part, it's a pretty sparse unit. And then overtopping that, we have the Bonwell Hill submember, which is another limestone package, pretty similar to Southgate Hill bed in the sense that it's got a lot of the Cincinnati Cincinnatus, this guy here. And it's our boundary between the C5A and the C5B. So it's another TST unit. So this is what the Southgate Hill bed looks like in one of its more proximal localities. So again, we have the C4, C5 boundary. We have this nice thick ledge overlaying the Arnheim, or Reba as it's called in the proximal settings. The Low Fort Ancient shale looks is far more interesting, I think, in its proximal setting than it is in its distal setting. We start seeing these large coral heads within it. If you look at some of these more prominent ridges, you see abundant pieces of trilobite, flexiclamine specifically. And you can also find a lot of these dasyclad algae as well. So it's in many ways more interesting faunally to look at the proximal than the distal, which is often unusual for some of these units. And then the Bonwell Hill, which again marks the C5A, C5B boundary, translates into what we call the Fisherville coral beds in more proximal settings. And so that's what we're looking at. Well, we're looking at that down here, actually. My apologies. So we don't find corals in it everywhere, but if you were to go to type Fisherville, you do find some nice coral beds in it. Alrighty. So some of you, especially the dry dredgers, will be well aware that one of the most attractive features of the Waynesville Formation and the Liberty Formation for many people is the presence of these butter shales. I'm only going to show you one of the butter shales because they all have the similar characteristics. So this one specifically is the Harper's Run submember that caps the Fort Ancient member. Some of you will probably know it as the Triptosaurus dewsrai butter shale. When we were naming these submembers, we tried our best, and we didn't always do so, but we tried our best to stay away from naming them after fossils, because in many cases, when you're working in, for example, the Harper's Run shale, which was formerly the dewsrai shale, you don't actually find Triptosaurus dewsrai. Another example, the Oldenburg submember, which is another butter shale, has sometimes been referred to as the Lyrodesma shale, which is a type of mollusk. And in many cases, you do not see Lyrodesma in the shale. So we try to stick to more name-based or more location-based nomenclature. But these butter shales are really interesting for a number of reasons. They get their name, their colloquial name of butter shale, because when they get wet, you can literally take a butter knife and spread them on an English muffin, as I did here. I don't recommend it, but you can do it. And because of that feature, when I was at this quarry, once this is a quarry near St. Leon, Indiana, I actually had to have the undergrad who was with me pull me out because it had rained the day before and my feet and boots had sunk into the mud and I couldn't move on my own. It's probably the closest I've ever gotten to stuck in quicksand that the 90s cartoons always warned me about. But these butter shales are really interesting because they have excellent preservation of fossils. Now, most people go looking for their trilobites. We get excellent flexiclamine. We get really nice Isotelus, which is a much larger trilobite. It's the state fossil of Ohio. But probably the most common thing you'll find in these butter shales are the various mollusks. The Ebonychia, Modiolopsis, you find lots of cephalopods. And then you can find some other interesting curiosities like conularids, lingulid brachiopods, and so on. And so the preservation in these shales are excellent, so it often attracts collectors to them. All right, so I will talk about what the proximal look of the Harper's Run butter shale looks like in a second, but I want to pair it with another unit. So we're going to move up to the Clarksville here first. So this is the entirety of the Clarksville at Cedar Creek, which is near Waynesville, Ohio. At the base of the Clarksville, we have what is called the Stony Hollow Creek subriver, also known as the Cincinnati Epiphyly bed. Back in the 90s, Fry termed this the Oniana or Oniella Epiphyly bed, which was the former name for this brachipod. And it's named this because during this time we have a really major proliferation of this brachipod. Now, as I mentioned before, we can see it in the Fort Ancient and some of these other units, but it doesn't really become mainstay until we hit the Stony Hollow Creek. And associated with the influx of this brachipod, we also start seeing small Platystrophias or Finlandistrophias. We see Eupinides, the horned coral Perwinkia, we see the brachipod Hiscobecus, and we start seeing a whole bunch of new taxa that we haven't really seen in the area before. And so this is what we call the Clarksville phase of the Richmondian invasion. It's where we really start seeing a major uptick in some new fauna. Most of the Clarksville we just lump together as the middle Clarksville. It's this sort of diffuse shaly package with limestones, not a lot of good packages to subdivide, so we sort of lump it all together. And then overtopping that, we have the Glyptorthus and Sculpta bed, which marks the base of the Blanchester member, and that is a very important, if not the most important bed, so I'll come back to that one in a moment. So I know Cameron's in here, so he's the real expert on this topic. But the Harper's Run submember, so the Butter Shale, and then the overlying Stony Hollow Creek submember, when you get to the more proximal settings, turn into the Cyphotriper Shale and then the BBB bed, or the Ball Bryozoan bed, respectively. And it's called this because you can find an abundance in both units of this bryozoan called Cyphotripa. And it's a rather interesting bryozoan. It again comes in as part of this Richmondian invasion. And when you flip the bryozoan over, you can see the remnants of mollusks that it had encrusted in life. And so when you see this in the proximal setting, it's very distinctive, and it's what the Harper's Run and the Stony Hollow Creek correlate into. All right, so the last unit I want to bring up briefly here is the lower Glyptorthus and Sculpta bed that I had mentioned previously. This is important because it marks the boundary between the C5 and the C6, so the next major sequence. And the mid-Richmondian conformity underlies this unit. Now, this unit, much like the South Cape Hill, can be sometimes diffuse and hard to identify in certain locations, but it does have a really distinct fauna if you can find it. The main brachipod, of course, being Glyptorthus and Sculpta, and then an even more rare brachipod, Catazyga hedi. Catazyga is great if you find it because it only occurs in 30 centimeter, so roughly a foot range throughout the Cincinnati Rex. Glyptorthus does make an appearance later up in the Liberty, but you can usually figure out which horizon you're on just based on context of other fossils and so on. So just a quick summary of what some of this looks like in one of the proximal settings. So we have much of the Fort Ancient components here, overtopped by the basal upper ravelin. So this is the equivalent to the lower Glyptorthus, the Sculpta bed. So the MRU, and what you can see here is that it's chopped out almost the entirety of the Clarksville. So this, again, is just demonstrating that this unconformity is pretty sizable. And so as I insinuated earlier, one of the questions we're interested in is this unconformity strictly a local thing, or is it a global event? And the natural first place to look would be, of course, in Tennessee, one of our adjacent paleobasins. And so this is a diagram from, I believe it's 1949, diagramming a series of mile-wide channels that can be found in southern Tennessee. They're about 100 feet or so deep. And what's really interesting is underneath the Fernvale limestone, so the base of this trap surface, we can see some of those fossils we talked about before. Cincinnati miki, we can see Eupinides, and then overtopping that, we see Richmondian fauna yet again. So what we're having is essentially 100 feet of erosion within the Waynesville Formation equivalent in an adjacent paleobasin. So it's Waynesville here, 100 feet of chop, and then Waynesville again being deposited within it, which is really quite remarkable and exciting. And Carl just informed me recently that there's been a new outcrop of this exposed, so I'm hoping to be able to go see that at some point and get a look for myself. And then, of course, as I mentioned, I did spend some time in Europe, and one place that I had the pleasure of visiting was Estonia. There was another geology conference, and since I was already in Europe, it made sense to go there. And as part of this trip, we got to go to various quarries and so on. And one of them was in a formation that locally they call the Sonia Formation. Now, based on chemostratigraphy, which I'll be talking about next, as well as the biostrat, so the conodonts and the graptolites and so on, they've been able to correlate the Sonia formation and its correlatives in Sweden to the Waynesville of the Cincinnati Arch. And what's really fascinating about the Sonia unit is that during this formation, they had significant sea level drop to the point where they had major paleokarst development. This is what the paleokarst looks like in core. And so we have, significant, again, significant sea level draw, significant chop in another paleobasin, but in this case, in a completely different paleocontinent. This is, the group of us at one of the quarries, and in theory, so I'm sitting right here. There's Carl, Dr. Huff's over here, Andre, Dr. Desrochers is right up there. So a few familiar faces for you. But my feet are in theory sitting right where this mid-Richmondian unconformity would be in Estonia. So discovering this was really exciting. And I'll come back to that more a little bit later. Right. So for the remainder, or most of the remainder of this discussion, I want to move into some chemostratigraphy, specifically carbon isotopes. That's what 2 out of my 5 chapters was really focused on. I'll explain what some of these terms mean in a little moment. But basically, some of the goals that I had while doing this part of the project was, can we refine the details of the Waynesville isotopic carbon excursion, or other words, ICE. And so if you see ICE, that's what that means. Can we trace those fine details to other paleobasins? And how do the details of the Waynesville excursion line up with the Richmondian unconformity, the Richmondian invasion, and all these other things that we've been discussing? Excuse me. So this is a generalized curve of carbon isotopes for the Ordovician. You see right here with the yellow arrow, the word Waynesville. So within the Waynesville, we do have a major carbon isotope excursion. And so these curves are made up of a series of positive peaks and a series of negative peaks. Generally, the positive ones are the ones people focus on. And carbon isotopes, in simple terms, are based on looking at carbon-12 and carbon-13, which are 2 naturally occurring isotopes of carbon. And so organisms, various organisms, they preferentially take up carbon-12, the lighter isotope of carbon. So during periods of high productivity or high organic burial, you will expect the rock material to have a higher isotope value because there's more organisms taking up that C12, leaving the reservoir enriched in C13. Contrary, if you have periods of low productivity, you have less C12 being incorporated, and so you may expect a lower isotopic signature as there's more C12 in the reservoir. Now, you can make some environmental predictions or assumptions based off the curves. We're using them strictly or primarily as a correlative tool. Because the carbon system is a global system, we can see a lot of these excursions across paleobasins, across paleocontinents. So for our purposes in correlation, it can be quite useful. So in 2010, Bergstrom et al. Produced what has become really the global standard for the upper Ordovician carbon isotope curves. And he did this using a series of outcrops and cores. So it is a compilation of different locations. And just to highlight here in green, we again have the Waynesville Formation. Oops, okay. Below the Waynesville, he did identify a series of additional positive excursions. The main one being the Geiss, or the Gutenberg isotopic excursion. This probably is the one that gets some of the most airtime. It's one of the largest. It is found in many locations, and so people tend to focus on that one. There are two smaller ones, the Cope and the Fairview. And then, of course, we get up to the Waynesville excursion. And even at this broader scale, we can already see some interesting details about the Waynesville excursion. There appear to be 3 primary peaks. We have the first one here at the base of the Waynesville, which is 2-pronged. We have a second one in the middle of the Waynesville, and then we have a third one here right at the top of the Waynesville. So we have 3 primary peaks with seemingly decreasing isotope magnitude. Now, over here at the Liberty, I have this point circled. Now, I'm a proponent that the negative spikes are just as important as the positive spikes. Now, a lot of times people don't spend too much time with the negative excursions. They can often be removed from underneath sequence boundaries. They're often thought to be artifacts of subaerial exposure, or they're basically artifacts of the sequence strat. But I think, and I hope will demonstrate with the subsequent slides, that these negative points can actually be quite correlative and useful in that manner. And so I've termed this point here specifically as the Liberty Low. If you look at Bergstrom curve, it is the most negative point in the curve. And while looking at curves from other paleobasins, it's quite prominent. It stands out well. So I think it's an important one to keep in mind while we do these correlations. And then over top the Waynesville, we have a couple more excursions with the Whitewater and the Aucoin. And then absent from the Cincinnati Arch is the Heiss, or the Hernantian isotopic carbon excursion. So the point of this project, much like the other aspects, were to try to refine this in the finest scale possible. So we have this broad curve that Bergstrom developed, and it's a very useful curve, but can we take that and subdivide it even finer and relate it to some of these other aspects that we're looking at? So to do this, I took a core from Cedarville, Ohio. It's the yellow dot up here. Selected due to its proximity to the type Waynesville, where we can see most of these submembers most clearly. And so from this core, we took samples every foot or so, so every 30 centimeters, using a hand drill, a DeWalt hand battery operated hand drill, and drilled out about 2 to 3 milliliters equivalent of powder to sample for isotopes. So this is the data set we came up with. And before I talk about the character of the curve itself, I just want to point out some of the different aspects. So we have the submembers that we discussed previously. And so these submembers were picked from the core based on our measurements of the lithostrat, so limestone, shales, etc., as well as looking at the fauna that we could identify within the core. The center portion has some of that faunal data. So these vertical lines represent the expected extent of certain taxa. So when we're looking at the Cincinnati Arch as a whole, where we would, what the range is of certain taxa that we know of. So for example, this line here is for Cincinnati amici, that brachiopod I keep talking about. We know we can find it as low as the Southgate Hill bed, but in this core, where we actually physically identified it, was right here where those dots are. So that's what those are showing. And then of course we have our isotope curve itself, which we then tried to apply some numbers to both positive and negative peaks, ones that we thought would be useful in correlation. So I just want to quickly highlight some of the taxa that we identified in the core that helped us make these submember picks. The first one here is in purple. So again, we have Cincinnati mikai, which again, we can see it in the Fort Ancient, but we know that in the Stony Hollow Creek or the Cincinnati Pibbly bed is where it becomes most prevalent. We see Rapniscina, which is sort of a dime a dozen brack. It's a wonderful brachiopod, but it is pretty prominent throughout much of the Ordovician, though it is a little bit more lacking in the Fort Ancient. So seeing it there it is of help. We see small Platystrophia with the Vinlandistrophia. And then we also see the brachiopod Eoconides. So these are a handful of those taxa I mentioned earlier that mark the Clarksville phase of the Richmondian invasion. So being able to see all these brachiopods together in the core is very helpful in understanding where we are in succession. Overlying that in the red, though, is really where the most excitement, at least for me, was. So again, we have Cincinnatina, we have Rapniscina, but then we have this brachiopod here, which is Glyptorthus insculpta. Now, if you recall from the beginning of the talk, Glyptorthus insculpta is that brachiopod that overlies the mid-Richmondian unconformity. It occurs in that horizon and then at the basal liberty, and that's it. And what's really sort of fascinating is when we try to find Glyptorthus in outcrop, even when we know we're looking at the unit it's supposed to be there, it can be hard to find. So the fact that we're looking at this 2 to 3 inch drill core, and it happened to go through a identifiable Glyptorthus insculpta at this horizon was quite remarkable. But it is one of the best tie lines we could ask for in the core. And then further up, we see another occurrence of Eoconides. Eoconides sort of proliferates in 2 horizons, one at the base of Clarksville, and then again up in the Liberty. I didn't really show you much of the Liberty, but the basal Liberty, we have another occurrence of Glyptorthus, and then we have 2 horizons of Eoconides, which separate a couple of different butter shales, the crinoid butter shale, and then the minuens butter shale. So we have some pretty good faunal constraints for our submember selections that we can then bring in and start correlating with our isotope curve. All right. So as with the Bergstrom curve, we can see the same 3 major peaks of the Waynesville. So the first peak we have in the Fort Ancient. It spans the C5A and the C5B, with the first prong down here in the Fort Ancient shale, I mean, and then the second prong in the upper part of the Bonwell Hill bed. We have peak 2 that makes up the majority of the Clarksville. So that's the 12B, 12A over here. And then we have the third peak at the top of the Blanchester, which is this 15A, 15B here. And so you can see that again here in the Bergstrom inset. We got the 2 prong at the bottom, we got the Clarksville one here, and then we have the Blanchester excursion there. And as I mentioned earlier, I find the negatives to be important parts of these curves as well. The 2 prong of peak 1 has this sharp negative named number 6. And then you can see this whole series of other ones here, which correlate, I would say, quite nicely with the Bergstrom curve, right where we'd expect them. And then we're up here at 18A and 18B. And I put a question mark here, and you'll see why in a few slides. But initially, when I saw this, I was like, there it is. There's the Liberty Low that I love so much. And it very well could be. We're certainly in the Liberty at this point. It's associated with these Eoconides, and it's associated with the crinoid shale. But as I'll show in a few moments, that may be a little bit more complicated than I originally had hoped. So for the Cedarville core, we've been looking at the distal setting. And so it makes sense, of course, that if we're doing this for the distal, we also want to see what it looks like in the proximal setting. We've done the work of correlating the various submembers from the offshore to nearshore. So it's important to replicate this in the proximal setting as well. And so the first diagram, the one we were just looking at, was from Cedarville. And now we're going down to High Grove, Kentucky, which is actually, in this case, a series of outcrops instead of core. And so you've already seen some of these images before, but just to give a little refresher, these next couple images are all from the High Grove, Mount Washington, Kentucky area. So this is that basal boundary, again, the Southgate Hillbed, or as it would be called out here, the base of the Rowland Formation. And that's our C4, C5 boundary. We have the mid-Richmondian unconformity up here underneath the upper Rowland. It overlies the Fisherville or the Bonwell Hill beds. And this is where we find those abundant corals. We also find this nice finely grained, what we call the green bed. It has a lot of green mineralogy in it and so on. And then moving further up, and so this image may be a little misleading. So this is the upper Rowland here, the uppermost upper Rowland, and then we have the Bardstown above it. Now, for the longest time, we always assumed that this was the boundary between the C6A, so the top of the Waynesville, and the Liberty, so C6B. Bardstown has always been, at least in our mind, correlative with the Liberty. And as I will show when we did the carbon isotopes, I think you'll find that it actually looks like the uppermost part of the Rowland is actually part of the Liberty as well, and which would make the Bardstown only the uppermost part of the Liberty Formation. All right, so here we have our two curves side by side, and a couple of details I need to point out. So we got Cedarville over here, we got High Grove on this side. They are at different scales, vertical scales, so that's important to know. So typically we do all our measurements in metric, of course, that's what science likes. But if you're working with a core from a geological survey, the core measurements, everything, all the details that they include with it are always done in feet. So typically when we're measuring cores, we stick to the measurements that they were done in originally, because that's what people are going to be looking at when they're comparing it to the core data. So we are in feet in the Cedarville here, and we are in meters in the High Grove. So just sort of keep that in mind when you're looking at the vertical scale. And so there's a couple things that we can point out right away. For one, you see peak 1 and peak 3. So that means peak 2, the one that we associate with the Clarksville, is completely absent at this point. It's been completely chopped away under the mid-Richmondian unconformity. Now we can still see peak 1, as I pointed out, but it definitely looks different. So we have the lower part, the lower prong, which correlates with the Fort Ancient Shale portion. And we have this upper portion as well, which is the Bonwell Hill equivalent. But that sharp -6, or that number 6 that separates the two, it's not quite evident. I mean, we certainly see an offset here, and I put the 6 there just as a reference point. But that appears to have been truncated itself underneath the Bonwell Hill / Fisherville, which is another TST. So you would expect a sort of sequence boundary under there. And that's what this little red line here is indicating, is that we do have some chop in the middle there. As mentioned, we got the MRU, and then we have a very nice peak 3 overlying that sharp negative we expect in the upper Blanchester. And then again, we have a very similar looking, what I was originally calling, and I still have it labeled as such, the Liberty Low. So 18A, 18B, it looks quite nice to what we see in Cedarville. But then if you follow the rest of the High Grove section up, we go even significantly more negative at the very top of the section. And so, of course, and unfortunately, I did not sample further up, though I think, if I recall correctly, Carl has recently done that, so we should get some data back soon. But it is quite possible that the actual Liberty Low may be a little bit higher in the Liberty. And this could be, I don't know, lower Liberty Low, or something silly like that. So that's one of those areas where we still have some more details to obtain, but at the very least, I think it looks quite nice that these are at least correlative, even if it is not the mainstay Liberty Low. And again, just pointing out, though, we can see some of these same negative points in the Bergstrom curve. All right, so I want to quickly try to go through this portion. So as Carl mentioned, I spent a little bit of time in Canada as a Fulbright fellow, which I never I never thought I'd actually get to be a Fulbright fellow. It was something that one of my undergrad professors had prompted me to do, and I eventually took the plunge to do it. And so, I have all this carbon isotope data for the Cincinnati Arch. We've got these nice fine scale correlations with the submembers and so on. And the next step, of course, is to go to a different paleo basin and try to replicate the same thing and see if we can see some of these same details. So to do that, I went to the Aucoin embayment, which is northeast of our present location, and looked at a core there. So while I was up there, I had the pleasure of Carl come up for a visit. I think it was actually in country working with another grad student on his work, but he came over to Ottawa to look at some Carlsbad with me. And unfortunately, as far as outcroppings go in the Ottawa area, for Carlsbad, this is about as good as it gets. It's this little rinkety-dink 2, maybe 3 meter section, but it still gives you an idea of what the overall section looks like. It's this alternating shale, silty limestone, and so on. And we did find some quite nice brachiopods while we're working in it. We found Eucanides, which I've mentioned a few times now. We found a Delmonella brachiopod, which is likely Cincinnati, so another good relative. And then we found the brachiopod Catazyga, which really got us excited. Because, of course, in the Cincinnati Arch, as I mentioned, Catazyga is only in a 30 centimeter bed. Now, as you'll see when I bring up the next slide, the Carlsbad is significantly thicker than the Waynesville is. So, looking at a 2 meter bed, we really can't say where we are in the succession. Well, it's nice to believe that we're standing on top of the Richmondian and conformity when we're here. I had a whole joke written about Carlsbad, Carl bad, whatever, but yeah. Anyways, so this is the core that we were working with. It's called the Russell core. This is the isotope data, which I'll get to in a moment. I just sort of wanted to give you an idea of what the core looked like. It's mostly this darker shale material. We get these nice accumulations of shale material. You can see a triangle right there. We can see some more turbid type sections here. And these little vials here are what we were drilling our sediment into. So again, just the bottom part of these vials are what we were drilling into. And so I zeroed in on the Billings and Carlsbad formation, in part based on the biostrat to start with. So Sharma and Dix, I think it was 2003, did a little bit of work on this core, the Russell core, and they identified a series of graptolites that are useful in our biostratigraphy. The most important one, in my mind, is Arnheimograptus anaconatus, and I apologize, I can never pronounce these things. But this graptolite is particularly important because it's named for where it was first found, and that is the Arnheim formation of the Cincinnati Arch. So that right away, that gives us a basal point. We know the Waynesville has to be above that and probably not too far above that. We also identified Amploplectrograptus, which is sort of it's a wide-ranging graptolite, but if we see it, we know we're in the right vicinity. And then Discelograptus up top, which marks where we usually see the whitewater formation. So if we get up that high, we know we've gone too far as the Waynesville is concerned. And then while going through the core, much like the Cedarville, I was trying to find any identifiable fauna and so on. And it was not as easy as the Cincinnati Arch. It's not quite as fossil rich. But we did see a couple things that were exciting. The first, again, I'll keep saying this, is Cincinnati mikai, that very important Waynesville brachiopod. And then much further up, we saw Eucanides, that other brachiopod I like to mention so much. And so with that distance in between, I was pretty confident that we were looking at somewhere in the Waynesville when we saw the mikai, and then we're probably, by the time we hit the Eucanides, probably in the Liberty interval. So if we look at the isotope curve itself, I think it supports that assertion. So in the base here, so we're actually in the Billings formation at the very base. We see the first prong of that 2-prong peak one with our sharp negative here at 6. We see the second prong, So that altogether is our peak 1. And right above it is where we're seeing Cincinnati amici. So based on the isotopes, a little low, not quite Stony Hollow Creek, more the Harper's Run, but it's still within the vicinity of where we expect this brachiopod to become much more prolific. We see the Clarksville curve, or the Clarksville peak 2, so 12A, 12B, that correlates with that there, with the sharp 11 below it. We infer where the mid-Richmondian unconformity would be based on the carbon isotopes, though we don't actually see evidence for it in the curve or in the core. And then we have a sort of an unremarkable looking, but what would be peak 3 here at the top of Blanchester. But what really stands out, I think, is the Liberty low associated with those Eoconides, just as we would expect. Because again, Liberty, we have these Eoconides, and we have the sharp negative. So I think it's a pretty nice matchup. When I first saw this curve, I was a little unsure, and then when I started placing these things side by side, it really started to come together. All right, so just quickly here, so we got our Cedarville core, we got the Ottawa core that we just looked at, and then we have 2 other curves here. So Anacostia Island, which Carl mentioned I had the pleasure of visiting. It's a small island north of Quebec. Beautiful island. I can't wait to go back. More deer than people, which is great. But in Anacostia, the Katian, so the interval I'm studying, is incredibly thick. So one thing to notice is the scale bars. So in Cedarville core, the scale bar is 5 meters, but if you look at the same scale bar in Anacostia, it's 35 meters. So significantly thicker. Same with Ottawa, it's significantly thicker than Cedarville. And then we have Estonia, which is much thinner. So I tried to bring some of these tie lines that we talked about through, though it gets a little bit more iffy in these last 2 curves. So again, there's that point number 6, which separates our 2 parts of peak 1. We follow that through those 2 cores as we just discussed. And then, it gets a little bit more iffy here and Anacostia, maybe this is altogether that first half of peak 1, you get second half of peak 1 here. And then in Estonia, it's sort of a guessing game at the moment because what we see is basically 1 peak altogether. So the question is this only peak 1? Is it peak 2? Is it peak 3? Is it all 3 peaks amalgamated together? I would argue because we see that karstification in the Sonia there of Estonia, that we're probably actually missing a vast majority of the Waynesville equivalent, and we're probably just looking at that peak 1 of the Waynesville extreme. All right, so just to sort of quickly wrap up here. So we got the Richmondian invasion. I think I demonstrated at this point, it comes in a series of pulses. It's not all at one. We see some coming in at the Bonwell Hill member. We see those corals in the proximal environments. We have the really nice Clarksville phase that comes in at the Stony Hollow Creek. And then we have a smaller phase that shows up with the Glyptorthis and Spelta, Glyptorthis, Catazyg, and a few others that I probably didn't mention. And these pulses do look different from the distal and proximal settings. We have different critters coming in differently depending where we are along the ramp. As of yet, I'm not confident in saying that we've identified the Richmondian invasion in other paleo basins. It's suggestive in the Ottawa embayment with the presence of the Eoconides and Cincinnati amici, but I think more work needs to be done to verify that. But the nice thing about the work that I've been doing is we've started to set up the framework where that can be done. We now have this more fine scale stratigraphy, fine scale chemostratigraphy, fine scale sequence strat, so we can actually start asking these questions in the other paleo basins. We have the mid-Richmondian unconformity, as I mentioned, marks the base of the C6A, base of Blanchester. Eventually chops away the entirety of the Waynesville below it. It certainly seems to be that we can see the Richmondian unconformity in Tennessee, as well as Estonia and Sweden, which does suggest a global signature, which has its own potential implications. And despite the size or the magnitude of the Richmondian unconformity, it does not seem to correlate with the largest pulse or largest change in fauna. from the Richmondian invasion, which is curious. Typically, we associate changes in turnover with these sequence boundaries. So you would expect this larger sequence boundary to have the largest faunal impact, but it does not appear to do so. And then the Waynesville isotopic excursion contains 3 primary peaks that are punctuated by all these sharp negatives. These negatives are typically associated with these TSTs, these limestones, and they are quite correlative, as I think I've demonstrated. And through our work on the Ottawa core, we can show that a lot of these fine details can be correlated with other paleo basins if we have a fine enough detail curve. And then there's that Liberty Low, which for the moment we will place at the crinoid shale in the basal part of the Liberty. So that is obviously open for some debate, and hopefully our new data will confirm one way or the other. So I'd like to thank you all for coming to my dissertation defense, and I'm ready to take questions.
All right, thanks very much, Chris.
So what do you want me to do? You want me to put my face back up here or keep the, well, I guess my face is up here anyways, but.
Yeah, I think, folks may want you to go back to some various slides and you can, why don't you just keep the screen as is? And, that means I can't see everybody's hand being raised or the other indications of wanting to ask a question, but let me just open the floor for questions, and maybe we could start with non-committee members, and maybe we could even start with non-UC people first. So if you have a question, just get it going. Dr. Freeman, any?
I would ask a question, but there's a lot of noise going on in the hallway next to my office, so I'm trying to stay mute.
We can hear you fine now. Rebecca, do you want to go ahead? Are you going to mute? Okay.
Oh yeah, they're repairing the water fountain outside my hallway, so I'm gonna stay mute.
Okay. Anyone else would like to jump in? Grad students who are present? Well, we don't want to hand this over to the committee. How about Tom Algio? Always ask good questions.
Okay, Chris.
Yeah.
I posted my comment. I didn't get a sense of what caused the MRU. I mean, you've discussed it extensively in terms of the temporal considerations and such, but what exactly produced it?
Well, so that is still one of the questions that I'm looking to explore. I'm of the opinion or belief that it's probably glacial eustatic, since we are seeing it in multiple paleo basins and on multiple paleocontinents. Though, of course, we don't have any nice glacial deposits found or anything at this time to really confirm that. So it is one of those things I want to keep trying to trace this to some of the other paleo basins I haven't looked at yet, seeing if I can zero down what that might be. Obviously, if you only see it, go ahead.
You showed a cross section from somewhere on the eastern margin of North America that suggested, if I got it right, that the section was more continuous in shallow water areas and the unconformity cut into the deep water facies. Is that correct, or did I get it backwards?
Yeah, so I'm not exactly which diagram, but
early on.
Yeah, let me
where you showed the.
Let me get out, see if I can get out of the view here. But yeah, what we generally see is the chop is more prominent in the proximal environment.
Okay, so
was it this
one?
guy?
Yes,
yeah,
that's right.
Yeah, so we're more proximal over here.
To the right.
Yeah, to the right is
okay.
The southern part of the arch, and so we're seeing more significant chop in that direction.
Okay. Do you see any evidence of stratigraphic condensation associated with that unconformity anywhere?
Not really. I mean, we do get some nice hard grounds in some of the proximal deposits. And it is associated with these nice limestones in the distal, but yeah.
Okay. How about karst features? That was mentioned very briefly. I see that some of the units that have been truncated are carbonates. Do you get clearly developed karst in those units?
Not here in the Arcs, not that I've seen. Obviously, in Estonia, that's the whole big deal is the karstification. But I have not seen any karstification at this horizon here.
Okay, very good.
Thank you, Tom.
I might just clarify
Yep.
slightly that in the channels, which were never connected with anything else, but there are clasts that represent the whole range of strata going back down through even below the stuff you show into the Lexington equivalent. But it's not really karsted, probably because most of that was mixed shale and limestone. The basal, here, I'm showing it with my cursor. Can't you see that? Basal lag has quite a range of class. And there's a second sea level drop surface within there too, which also has class, but isn't as severe. It probably is associated with the Liberty base. All right, sorry.
I have a question.
Irina, please go ahead.
Yeah. Hi, Chris. Thanks for the presentation. I was wondering if you could comment on the carbon isotope curves that you have narrated in some of your sections.
Yep.
And if you could explain what are the environmental factors that would cause those carbon isotope excursions, and if those changes are going to be rather local signals or a more global signal, because you're using those curves to correlate sections, and I was wondering if you can comment on that.
Right. As I mentioned, the carbon isotopes are, of course, a global system, but they can have a local impact. If you have a more restricted basin that's not quite as connected to the overall global marine system, it can have its own distinct signature. And so one thing that people postulate when they're looking at these isotopes is that when you have these positive peaks here, so as I mentioned, that's where you get you're sequestering a lot of the C12 due to high productivity and so on, that these could be periods of lower global atmospheric temperatures. So you have lower atmospheric carbon, and so they will often interpret these to be cooler temperature times. Whereas in the negative peaks, where you have low productivity, you would have more carbon in the atmosphere and thus potentially higher temperatures. So that's some of the environmental things that people do discuss with it. Again, we're using it primarily as a correlative tool, but it is important to note that these curves can have that regional effect when we're looking at things, and that might explain why it's not always a one-to-one correlation as we may like it to be.
And Chris, that's how you rationalize when you had the slide towards the end, which had that had 4 or 5 carbon isotopes.
Yes, yeah.
They're offset, right? So one negative or one positive is like plus 0.5, another one is at plus 0.1, another positive is at maybe even 0.
Right.
Right. So you rationalize those differences by these local factors.
Correct. Yeah. So they're not always going to come out at the same number, but what we're trying to look for is the magnitude of swings, the change from the lowest low to the highest high, and so on between point and point. And look at it. It doesn't sound so sophisticated, but in many regards, it is pattern matching. But it's pattern matching and associated with, the biostratigraphy and the lithostratigraphy and all these independent factors.
The other thing that struck me, and I always think this, about you never see anybody trying to replicate one of these curves, right? So you don't take samples of a core and measure them 2 or 3 times, the same samples.
Mm-hmm.
And who does that in other sort of endeavors of chemistry? You don't determine the age of the same granite 6 times to to get the same number. So
and not that analyses in other fields are inexpensive, but it's in part because doing these carbon isotopes for a curve can be quite expensive. One thing that I didn't mention is we do take oxygen isotope samples as well. It's the same sample, but they run them for oxygen as well. So as long as the oxygen isotopes and the carbon isotopes do not, if those curves don't converge, we typically take them as true, that they're good values. But yeah, it would be interesting at some point to take one of these curves and drill 2 or 3 samples from each horizon and see how different it is even within the same core.
I'll jump in on a comment. I did that, and it was it matched kind of okay, but I actually did a coarse sample and a fine sample. And the fine sampling, I mean, pulled out a lot more information, but it didn't exactly match the coarse sample. If I can jump in here while we're talking about isotopes, I was looking at the negative isotope ships that you had, and noticing that they didn't really correlate with sequence stratigraphic position, at least in the kind of order of the sequences that you have on here.
Right.
In your dissertation, part of your dissertation that you didn't talk about, you had the where you were looking at multiple order and kind of constructive and destructive interferences. So do you think there's any of that here with your negative shifts, or do you think it's like completely separate?
Well, that's a fascinating question. I hadn't even really thought to compare it, because while going through this, I was noticing that a lot of these negatives, they seem to be within TSTs, but sometimes they're at the top of the TST, sometimes they're at the base of the TST. And it would be really interesting to take that model that I came up with of this different orders and see if that can explain where these negatives are falling at any given point. That's a really good idea. I appreciate that. I'll write that one down.
More questions? None in the chat. Anyone? Before we move on to the committee, anyone else? All right, how about then from committee members? Ben? Or
at the moment.
Or Warren, if you're still Carl?
Sure. I have many questions, of course, and there's much that still needs to be discussed, but not all could be done here. I must say, but before I go ahead and say a couple of things, though, Warren emailed that he had a conflict that arose, so unfortunately he's not here. I tried repeatedly to reach Andre, and unless I missed something, he's not responded, so I feel badly about that. But
And excuse me, Carl, Arnie had to leave at 1 o'clock.
I see.
Yeah.
Anyway, so
so I have a committee of 3 now.
let me say one thing though. Perhaps Chris, you could say just a few words about the work you did on the gastropods, since that really didn't come up here. But perhaps you could just very briefly summarize some of that.
Let me find a good slide for it. Had a better slide. Let me see.
Yeah, not any great details. Obviously, you had to cut that, but
Well, I'll just put this one up because this one's visually appealing. So one of the units that I was looking at with Ben is a unit called the Marble Hill gastropod beds. And so there's actually 3 horizons. One's at the Southgate Hill bed at the base of the Waynesville. There's one at the base of the Clarksville, so the middle Marble Hill bed, and then there's one at the basal Liberty, so Upper Rowland. And that's what we're looking at here. And what's interesting about this unit is because typically when we look at Paleozoic gastropods or mollusks in general, the shell structure of these gastropods is completely obliterated. They're composed of aragonite originally, so after death, the aragonite quickly turns to calcite, and a lot of that original shell structure is obliterated. But what we have in specifically the Upper Marble Hill bed is excellent preservation, where you can actually see some of the relic shell structure of these gastropods, even though it has in fact been recrystallized as calcite. And so what that chapter, and it's the last chapter of my dissertation, was focused on was trying to figure out why these snails were preserved in the way they were. And in short, the basic premise was, so we found gravitational cement in some of these thin sections of the upper part of the Marble Hill, which suggests we're in some sort of likely marine vadose zone, so that these gastropods are not completely submerged with water all the time, and so that slows the rate of the aragonite dissolution, and so only small bits of the shell are dissolved at a time, and thus only a small bit is recrystallized as calcite at a time, which allows this high fidelity preservation to occur. That's the 1 minute clip note.
Yeah, sure. Well, thanks for the brevity on that, but also just let me say, I think I've always had a question about that model, because one would think that exposure to the atmosphere and vadose, rainwater and so on coming in would tend to actually destroy the fabrics more readily rather than help to preserve them. So I know we've discussed this, but perhaps you could consider what factors might allow this to be effective if it is in fact this model.
Right. So with these Marble Hill beds, I should have mentioned we are in a proximal environment, so we're fairly near shore. But if you remember our paleogeographic map, we're 20 degrees south of the equator, so we're in an environment that was likely fairly arid. So we're likely not getting too much rainwater occurring, and so we know we're vadose because we have the gravitational cement. So we know there has to be occasional water percolating in. So if we're not getting rainwater, then there has to be seawater is what's coming in, occasional extra high tides or whatever it may be. So in my mind, the reason why we're not getting that shell destruction from meteoric water is because we're really not getting meteoric water present because we are in such an arid setting.
Well, you have the dripstone cements, so
Yeah.
obviously there must have been some vadose action going on in
Right.
there. If it's restricted enough, perhaps. How do we have any sense about how rapidly the recrystallization to calcite with this kind of high fidelity can take place from the modern? When you talk about this, I seem to remember some kind of discussion of this sort.
Yeah, I mean, I can't really put like a time scale on it per se, but I do know that we can look at the Bahamas, for example, and you're all probably familiar with the large conch shells that you can get from the Bahamas that everyone likes to decorate with. But there's some Pleistocene versions of those. I'm pretty sure it's Pleistocene, where when they look at it in thin section, they can actually see a line within the shell where it's high fidelity calcite preservation on one side and it's still aragonite on the other. So the whole shell is not being transformed all at once. It's happening slowly throughout. So I suppose you could take something like that and maybe get a estimate of rate, but it can certainly take quite a bit of time.
No, I think
Dan, if I can jump in, Carl, sorry. Dan Sturmer wonders whether are there any similar examples of preservation in the Persian Gulf?
I haven't looked there. That would be an interesting thing to do. This is one of those projects that, part of why I didn't include it in the talk was it is sort of a side shoot. It's related from the sense of stratigraphy, but this fine detail is a little something different. But ever since I've started on this project, I've been fascinated with the preservation of some of these Paleozoic snails. So I've been wanting to look at other snail deposits. I looked at our Hernangian, so End-Ordovician one in Anacostia Island, which shows what you would expect to find complete obliteration of the shell structure, even though it is a bed that's made up almost entirely of snails. So I'm not familiar with the specific deposit, but it'd be interesting to see that.
It's a stunning photomicrograph, Chris. And Carl, please continue.
Just to address that, I don't know of any Persian Gulf, but as he said, there is some Bahamas work that's been done. But also to try to tie it a little bit more to the bigger story here, each of the three tongues of Marble Hill, it's not very good terminology, but sits above one of the sequence boundaries. So, and one in particular over the MRU. So these things do appear to be early transgressive deposits that are coming in as shoal facies. And so there is a tie to this whole story. And the other thing is, of course, that they are traced in an up ramp direction into stuff like Rowland, basically into Rowland or analogous facies, which are very odd facies. I know you didn't have time to get into that, but they are peculiar, being so barren of fossils, many of them, and also, but occasionally having corals and restricted fauna like ostracods. So there's perhaps, I know there was originally a quest to try to figure out what was making these peculiar environments at the time of this mid-Richmondian, but there are other things too, mineralogical issues that could be brought out. But time is what it is.
Yeah.
So,
endless questions for days.
Oh yes, I have many more. But I'm not going to stop, of course, with those questions because we need to get these things shored up for papers in due time. Yeah.
Any other questions from any participants? Dan Sturmer has one in the chat, but let's see if there's anyone else first. Okay, Dan had a butter shale question.
Okay.
I did, and it's related to and you didn't talk about it here, but in the dissertation where you had the kind of constructive and destructive interference in sea level to describe, when you're getting butter shales, but presumably, like that's happening everywhere, right? So can you comment on your ideas about what's so special about the tri-state that you get so many of these, whereas even if you're in a similar position, marine position, similar depositional environment, you don't see them all over the place at all times.
Right. So I think the main thing has to do with your proximity to sediment source and so on. So for example, take New York State, the Devonian New York State, we find excellent, I wouldn't necessarily call them butter shales in the sense that they're gonna turn back into mud and get stuck in them, but they have the same type of excellent preservation of trilobites and so on. And so we do see the same type of preservation in these different settings. But I think the characters that make the butter shale itself buttery is in part based on our source, or what our source is, and our proximity to the source. So we're getting a lot of clays coming here, and of course clays like to swell in when wet, as opposed to maybe fine quartz or something like that, or fine carbonate mud. So I think in part it has to do with that, where we are in the basin and what we have being brought in.
Okay, anyone